Welcome to The Explainer. Right now, we are standing at the absolute bleeding edge of artificial general intelligence. We're looking out at a future that honestly feels almost tangibly cyberpunk. We are finally moving beyond those sterile, climate-controlled server farms of the cloud and stepping right into the gritty, unpredictable, physical world, the world of edge-native autonomous agents. So let's unpack the architecture that's actually making this possible.
It's a fascinating question, isn't it? What actually happens when you take a massive, multi-billion parameter AI, a system totally used to infinite cloud compute, and you trap it inside the physical, battery-starved body of a robot? Well, the dystopian reality is it completely fails. Current AI paradigms, particularly pure deep reinforcement learning and large language models, hit a hard wall the second they enter the physical world. They suffer from severe thermal limits, crippling memory constraints on edge devices like the NVIDIA Jetson Aura Nano, and a frankly terrifying tendency to hallucinate physical actions. The research makes it crystal clear. Trying to force a slow, massive, power-hungry brain into a fast, vulnerable body is just a recipe for disaster.
Okay, so to solve this, we need a massive architectural paradigm shift. The traditional transformer and LLM paradigm relies heavily on completely opaque multi-layer perceptrons. It's incredibly power-hungry, it suffers from catastrophic forgetting, where learning a brand new task just wipes out the old ones, and frankly, its reasoning is a total black box. But there's a revolutionary new approach presented in the source material, the FGSGR framework. It is explicitly interpretable, highly efficient, and designed from the ground up for continuous learning in localized environments. We're talking about moving from brute force block building to a truly elegant adaptive architecture. This architectural gap is stark. The standard LMM paradigm is basically a single-pass, feed-forward chain of discrete tokens. It results in distributed entanglement and is basically reborn every single time you open a new context window. But the FGSGR architecture is completely different. Instead of a straight, finite line, it uses cyclical, multi-frequency factor graphs. It's a continuous, compositional belief system that actually maintains its identity over time.
So, what exactly is this FGSGR acronym the researchers keep using? It stands for Frequency-Governed Self-Graph Reasoning. I know, it sounds super heavy, but just think of it as the biological skeleton and the foundational substrate of a perfect autonomous agent. It beautifully integrates factor graphs to represent beliefs, the minimization of variational free energy to drive action, predictive coding for neural implementation, and, this is crucial, a strange loop of self-referential metacognition. It doesn't just process data, right? It actively monitors its own processing.
FGSGR isn't just a single algorithm. It's an entire interconnected assembly. You have the representational substrate using factor graphs, the objective function minimizing free energy, and the neural implementation via predictive coding. But where the magic really happens is in the temporal organization using tri-frequency oscillations. It is genuinely awe-inspiring how this works. The system processes immediate sensory details at lightning-fast gamma frequencies, behavioral patterns at theta frequencies, and stable core beliefs at really slow delta frequencies. It's literally acting like a living engine.
But here's where we push into entirely new territory. To make FGSGR work perfectly on tiny edge devices, the architecture integrates it with CANEs, or Kolmogorov-Arnold networks. Instead of traditional neural networks that use static, black box nodes, CANEs do something wild. They shift the nonlinear learning functions to the edges of the network using dynamic, one-dimensional, human-readable B-splines. Imagine these as the glowing digital nerves of our agent. The nodes themselves, they just do pure, simple addition.
The crucial point here is what this means for safety. By shifting the complex math to these edges, the framework achieves absolute white box interpretability. With standard MLPs, the shape of trust is smeared across thousands of hidden layers. So if a robot makes a mistake, you literally can't audit why. But with CANs, the precision of any belief update is mathematically explicit. Because the nodes use pure Holonic summation, the signal doesn't degrade. This allows for rigorous, auditable safety protocols. If a failure occurs, we can track it down to the exact mathematical geometry. No more guessing.
Let's see how this all builds into what the research calls the metabolic compute loop. Remember, an edge device like a robot has limited battery and compute. It has to manage its energy like a living, breathing organism. When the agent senses a physical anomaly, say a slip sensor on its actuator fires unexpectedly, its metacognitive layer registers a massive spike in urgency. To learn from this, it dynamically expands the topological grid of its B-splines, allocating compute to solve the problem. Once it figures it out and reaches geometric homeostasis, an aggressive mathematical penalty called L1 regularization literally prunes the grid back down. It expands to learn and prunes to survive. It's treating compute as a finite metabolic resource, which is just brilliant.
Actually, that leads to one of the most mind-blowing features of this entire architecture, symbolic freezing. In traditional deep learning, you have to maintain massive matrices of weights in memory forever. It's so wasteful. But in the CAN FGSGR system, when a topological edge learns behavior and achieves long-term stability, it literally freezes. It uses symbolic regression to collapse that complex spline into a highly efficient compiled mathematical equation, something simple like y equals sine of x squared plus c. It literally bakes the learned behavior into low-power math, freeing up critical compute cycles to look at brand new sensory data. It's an efficiency trick that fundamentally changes how we think about AI memory.
Okay, so we have a fast, efficient physical body now. But what about high-level reasoning? This brings us to the sensory-motor grounding problem. LLMs are amazing at semantic knowledge. I mean, they can write poetry, code, you name it. But if you plug them directly into a robot arm, they hallucinate and break things. On the flip side, pure active inference excels at physical motor control, but it really struggles with abstract, zero-shot logical reasoning. We somehow need to merge the fast physical body with a slow, wise mind.
To pull this off safely, the framework enforces strict dual-process cognitive stratification. Think of the famous psychological concept of System 1 and System 2 thinking. System 1 is our CAN-FISGR engine. It runs locally at blazing fast speeds, like 1000 Hz. It handles all the real-time sensory motor control and reactive survival. System 2 is the LLM. It's relegated to the top level, running slowly, asynchronously, acting as an off-policy semantic oracle. And why is this separation so critical? Because it guarantees the robot's survivability. If the LLM goes offline or hallucinates some completely illogical directive, the fast System 1 simply rejects the top-down command because it contradicts bottom-up physical reality. The robot stays completely safe.
But wait, what happens when System 1 encounters something totally alien, a completely novel environment that surpasses its localized learning capacity? Well, it calls out to System 2. It sends a structural prompt to the LLM. The LLM then generates a high-level declarative strategy, which is compiled down into what's called the alpha prior. The LLM basically drops a brand new structural base function right into the agent's graph. This is a game changer. It instantly recontextualizes the robot's entire worldview, allowing for zero-shot behavioral adaptation. And because of the localized factor graph, this happens entirely without the catastrophic forgetting that plagues classical neural networks. All the old knowledge stays perfectly intact.
So, let's pull this whole shebang together. What we're looking at here isn't just an iterative software update. It is the blueprint for the ultimate edge-native agent. By synthesizing Kolmogorov-Arnold networks, the FGSGR cognitive framework, and an off-policy LLM, we get an organism that strictly adheres to the metabolic limits of its hardware. It learns continuously and resiliently. It perfectly stratifies fast survival reflexes from slow semantic reasoning. And above all else, it operates with absolute, auditable, white box safety. We are finally moving past the brute force black box parameter scaling of yesterday.
Which leaves us with a truly fascinating question to end on. We've solved the black box. We've solved the metabolic constraints. We've merged high-level reasoning with incredibly safe physical embodiment. So if we successfully deploy these resilient, self-monitoring, white box autonomous agents into the physical world at scale, what limits truly remain for artificial general intelligence? It's an absolutely incredible frontier. Thank you for joining me on this explainer, and I highly encourage you to keep exploring this amazing architecture.